Jnanam paramam dheyam. Knowledge is supreme.
Hello students. In the last lecture, we had seen that how do we assess stability of closed loop systems using Laplace domain, and we saw that whenever the closed loop system has any dead time, so maybe that dead time is from the process itself, or it may be a dead time because of a delayed measurement. Both those cases we cannot analyze the stability accurately using Laplace domain, and we have to approximate the dead time by using Paddy's approximation. And I had said that even though you get some stability limit for that system, if we implement that controller gain or slightly lower controller gain than that, you might end up still destabilizing the system, and that is an approximate analysis. So in this lecture we will see how we can correct for this and how do you perform a more accurate stability analysis by using frequency domain analysis. So that was one of the limitations of Laplace domain analysis. So the first one is delays have to be approximated. That means they cannot be handled accurately. And second limitation of Laplace domain analysis is that for a given transfer function, let us say even though we do approximate analysis and we get the stability criteria, they are all dependent on this process parameters Kp, tau and Td, and there is no guarantee that if there is some error or these parameters deviate, which in reality is quite often the case, then in that case whether that feedback system will still be stable or not, those kind of robust analysis cannot be done using Laplace domain analysis. So if there is some variation in the parameter, maybe it is a plant model mismatch, it does not tell me how much is the tolerance in terms of this controller gain or time constant or delay time, which can still I can confidently say that the resulting system would still remain stable. So both these limitations can be rectified if we perform the analysis in frequency domain, which is an inverse time domain. So when I say frequency domain analysis, what we are essentially interested in capturing what is known as a frequency response of a system. So this means we are going to calculate what is known as a frequency response. And when I say frequency response of a system, what I mean by that is you have a process which has certain inputs and certain output, and we say that at the input we introduce an oscillating input, so a sinusoidal input maybe of form A sin omega t, and when you do that it is hypothesized, or it is in fact true, that when you put in sinusoidal input into the system, the output after some time, after initial transient, would again be a sinusoid, and it may have a different amplitude and it may have a different phase. So the output is also a sinusoid. So the frequency response is based on this principle that if we input a sinusoid into a process, then the output will also be a sinusoid. But what is unknown is that if my input is of amplitude A, then output may not be exactly of amplitude A, so let us say if amplitude is B, then we define what is known as an amplitude ratio as B over A. So, it is the ratio of output amplitude to the input amplitude, and then we also calculate what is the difference in the phase between input and output. So, let us say input was 0 at this point, however, the output has this much lag. So, this is called as the phase, and we will see later that both this amplitude ratio and phase are functions of frequency. So, when we talk about frequency response, what we are actually interested in is calculating AR as a function of omega and this phase as a function of omega. So, when we get this, that is known as a frequency response of a system. Now, we had actually seen a response of a sinusoidal input to one system, and that was a first order dynamical system. When we were studying first order systems in way back in week 2, we had seen how does it respond to a sinusoidal input, and if you recollect what was our answer. So, if I want to calculate frequency response or frequency response of first order system, then what we had done was we had seen the process transfer function is Kp over tau s plus 1, and we had used input as A sin omega t, and then by using Laplace domain analysis by we had calculated what is Ys, which will be Gs times Us, taking the Laplace of this, and eventually we expanded it using partial fractions, and what we obtained as the long term response was Kp over A Kp over root of 1 plus tau square omega square sine of omega t plus phi, where phi was equal to tan inverse of tau omega minus tau omega. So, that is what we had obtained long back. So, in this case if we define amplitude ratio as amplitude of output to amplitude of input, we get amplitude ratio as Kp over root of 1 plus tau square omega square, and the phase as minus tan inverse of tau omega. So, you can see that both this amplitude ratio and phi are functions of omega. And when we do the frequency response analysis, we compute this AR and phi for all possible ranges of omega, that is for all omega from 0 to infinity. The motivation behind that is if you have studied Fourier series in mathematics, then you can recall that any periodic function can be represented as sum of sinusoids with varying frequency. So, what essentially in the frequency response we are doing is that by computing this AR and phi at all possible values of omega, we are ensuring or we are finding out how this system would respond to a sinusoid of any frequency. That means it can respond to any periodic function. And then if later on when we develop this stability analysis theory, we will see that then it will be able to capture the particular frequency which is going to destabilize the system, and what are the corresponding conditions for stability and so on. So, that is the motivation behind using frequency response and going from all the values and all we are interested in is how this AR and phi are functions of omega. So, previously for first order system we had seen how do you compute AR and phi. So, let us try to find a general method of how do you find AR and phi. So, we had seen a very fundamental method of finding this is that you take the transfer function of the process, you take the transfer function of input as A sin omega t and the Laplace of that, find the Laplace transform of the output and invert it, and it becomes a very laborious process, especially if the transfer function or the process has a much bigger or higher order transfer function. So, I'll now give you a very simple method of finding this AR and phi for any given transfer function. So, let us say if we have a transfer function GS, so this is any transfer function, and we want to find out what is AR and what is the phi, and what by that I mean what are these functional forms as a function of omega. So, what we do is we first substitute S equal to I omega, where I is the complex number root of -1 and omega is any frequency. So, when we do that we are going to get g of I omega. So, this is a complex number. So, we are going to get a complex number, and any complex number, if you recall your complex number mathematics, can be represented in the amplitude angle form as the amplitude of that number times e raised to minus angle of that number. So, you represent a complex number in the amplitude angle form, and then amplitude ratio is the amplitude of this complex number, and the phase is the angle of this complex number. So, as simple as that. So, let us now see what do you get if we apply it to the first order system. So, if g of s is kp over tau s plus 1, we substitute s equal to I omega, we get kp over tau omega I plus 1, and now we have to represent it into amplitude angle form. So, we will have to take out kp as common, and in order to make it into that form you will have to multiply by the complex conjugate of the denominator. So, we have 1 over tau omega I plus 1 into tau omega minus tau omega I plus 1 over minus tau omega I plus 1. So, this is a plus b, a minus b, so that is a square plus b square. So, we will get 1 plus tau square omega square as denominator, and this will be 1 minus tau omega I. Now, in order to find the amplitude, so this will be equal to kp into 1 plus tau square omega square, and this I can write it as root of 1 plus tau square omega square into e raised to minus tau omega I. This is cosine of theta, sine of theta. So, from that you can get this, and so the final form what you will get is kp over root of 1 plus tau square omega square e raised to minus tau omega I. So, as per the previous definition, what we are getting is this is amplitude ratio so, just a moment. So, this is sine phi cos phi. So, this is tan inverse of this, and this is your phi. So, you recreate the same values of AR and phi as we had obtained by using the inverse Laplace method. So, this method is very simple method to find out the frequency response or amplitude ratio and phi for any transfer function. So, before going forward, let us try to find out the frequency response for some other processes. So, we will try to establish few results. So, one is if I have a process function, transfer function as a product of multiple transfer functions, which is very common in feedback systems when we have multiple systems transfer functions in series. So, what we are going to get is how do we get the amplitude ratio and phi for such a case. So, let us represent each of these as the amplitude ratio and phi. So, this will be mod of g1 I omega times e raised to power angle of g1 of I omega times mod of g2 I omega e raised to power angle g2 I omega, and similarly g3 and g4. Which on simplification we will get as, so g1 I omega, g2 I omega, g3 I omega and g4 I omega times e raised to power all the summations of these angles So, what we are seeing now is this is AR1, this is AR2, this is AR3 and this is AR4, and this entire product we are going to write as, so this eventually we are trying to say is amplitude ratio times phase. So, based on this what we can write is AR is equal to AR1 times AR2, AR3 times AR4. So, if we have transfer functions in series, then the amplitude ratio of the resulting combination is the product of all these amplitude ratios, and when we talk about the phase, this phase phi is actually, these are all phase 1, this is phase 2, this is phase of 3, this is phase of 4. So, phase is actually equal to the summation of the phases. So, it is a very important result that if we have a series combination of multiple transfer functions, then the final amplitude ratio is the product of amplitude ratios and the final phase is the summation of all the phases. So, let us use this for a very commonly used transfer function, which is first order plus dead time. So, if your transfer function is Kp over tau s plus 1 e raised to minus TdS, and if you recall, these are the types of transfer functions which prompted us to use frequency response because Laplace domain analysis was not possible, or Laplace domain stability analysis was not possible for such kind of a system, and we had to approximate this. Let us see now what happens when we have the frequency domain analysis for this system. So, we will call this as G1, this is G2. So, G1 is our very own friend first order system. So, we have AR1 as Kp over root of 1 plus tau square omega square, and phi 1 is minus tan inverse tau omega. G2 is e raised to minus TdS. So, in order to find its AR and phi, we have to substitute s equal to I omega. So, G2 of I omega is e raised to power minus Td omega I, which fortunately is in the amplitude angle form. So, what we have is the amplitude ratio of a delay is 1. So, that means if you have a delay, then if the sinusoid is input, you will get the same sinusoid as the output, which makes sense. However, the phase is different obviously because we are delaying the sinusoid. So, accordingly the phase is going to be different than the input. So, for a first order plus dead time system, so for G of S, the amplitude ratio which is the product of amplitude ratios which we get as same as the first order system, and the phase we get is minus tan inverse tau omega minus Td omega. So, you can see that the dead time is going to affect only the phase of the system, it is not going to affect the amplitude ratio. Okay, so with that groundwork, we will now move on to how do we represent the frequency response. So the frequency response can be represented in two forms. So we will see representation of frequency response and the first is a body diagram. So body diagram so in all these cases we have to represent AR as a function of omega, phi as a function of omega. So in body diagram we will have two sets of plots, one will be for AR and one will be for phi, and it is a so on one of the axis we plot log of amplitude ratio versus log of omega. So we will be having a log plot between amplitude ratio and omega, and I will come to the point why we need log plot. And the second one is normal versus log plot. So it is a phase versus log of omega. So we are going to plot two things. So the body diagram is log of AR versus log of omega plot and phi versus log of omega plot. And depending on which book you are referring to or which simulation software you are using, there might be different variations of these log plots, as in it may be log to the base 10 or it may be a decibel conversion. So all those things are possible. The idea is it will just shift the curve up and down. Many a times you would also have log of omega tau rather than omega as the x axis. So these are just different variations. It will just shift the curve either up or down or left or right. But essentially what you are interested in body diagram is how does the log variation, how is the log variation between omega and AR, and normal versus log variation of phase. So let us see if we have a first order system. For Gs is equal to Kp over tau s plus 1, our AR is Kp over root of 1 plus tau square omega square, and phi is minus tan inverse tau omega. So let us try to see how does the body diagram look like here. So if we take log of AR, we will have log of Kp minus half of log of 1 plus tau square omega square. So now if we take two asymptotes are possible here. When omega tau is very much less than 1, so that is a low frequency asymptote. Then we will see that 1 plus tau square omega square would be roughly equal to 1. So this second term would vanish and we will have log of AR is roughly equal to log of Kp. So it will be a constant, it will not be, it's independent of omega. So it will be a horizontal line in the body diagram. When we consider the other asymptote where omega tau is very much greater than 1, in that case we can approximate 1 plus tau square omega square as tau square omega square, and what we will have is log AR is equal to log Kp minus log of tau omega. So half and 2 will get cancelled. So it's a straight line in log plot. So that is why in the body diagram we plot we have a log plot between AR and omega, because then this gives you a straight line. So if we go back to a previous figure, so what we have seen is at low frequency we have almost a straight line, horizontal line, and at very high frequencies we have a straight line with a slope of -1. So typically for a first order system, the frequency response, the first part of body diagram will look like this, and the second part is simply tan inverse of tau omega. So, when omega is equal to 0, we have phase equal to 0. So, here we cannot show the omega equal to 0 is that other negative infinity. So, this phase is going to approach 0 as you have very low frequency. So, that will be the asymptote, and when omega tends to infinity, it's tan inverse infinity. So, what we will have is phase will be equal to minus 90. So, the other extreme is minus 90. So, this response looks like this. So, that is how a body diagram for a first order system will look like. And it can be constructed for any transfer function. Now, let us look at the second way of representing frequency response, and that is known as a Nyquist plot. So, here instead of computing two figures, we are actually going to compute a single to represent AR and phi in a single graph. So, in order to do that, what we do is we take frequency as a parameter, and then we plot locus of the complex number which was used to obtain this frequency response. So, we take g of I omega as a complex number, and we plot this complex number in a complex plane. So, this is the complex plane, and you simply plot how does this g of I omega moves into this complex plane as omega goes from 0 to infinity. So, let us see how would it look like for a first order system. So, for a first order system, when omega is 0, in that case what we have is AR is equal to, so if we see this figure, so when omega is equal to 0, what we are going to get is AR is equal to Kp, and this will be tan inverse 0, so it will be 0. So, we have a complex number which is 1 or Kp. So, when omega equal to 0, g of I omega is equal to Kp. So, it is a number which can be seen here. So, it will remain here, and then when omega goes to infinity, your complex number goes to 0 because AR goes to 0. So, eventually this trajectory is going to end at this point. However, for all the values of omega between 0 and infinity, the phase is always going to be negative, and the maximum phase is going to be 90. So, this will look like, the trajectory will look like this as you increase omega, and at any point in this graph, let us say if I am interested in this particular point, it will have a certain frequency, and the distance of this point from the origin is the amplitude ratio at that particular location or that frequency. So, if this is omega 1, this is AR of omega 1, and this particular angle will tell me the phase. So, this is the phase at omega 1. So, using a single figure we can represent the entire frequency response, and this is known as a Nyquist plot. So, we will take a short break here, and when we come back we will see how using this body diagram or a Nyquist plot and in general frequency response, how do we assess the stability of a feedback system. Thank you.